Okay. So if there's anything urgent that you want to bring up, then you just raise your hand and then I'll recognize you there. So input, output management and disk scheduling is a topic for Unit 5. It's Unit 5 in the study guide. And we will discuss the following concept, okay? So the outcomes are describe various categories of input-output devices on computers, explain the organization of the input-output function, explain DMA, or direct memory access, explain the different types of input-output buffering, describe disk scheduling, and define RAID and discuss the various RAID levels. Okay. Now, any computer, anything that you refer to as a computer, if you refer to it as a system, it must be able to trigger the following functions. We know input, process, and output. And for a computer, obviously, to some extent, computers do feedback to say when there's output, there needs to be feedback back to the input interface to report on the status of the particular transaction or whatever was being performed. So input output is something we see not just only in computers, you see it everywhere. Okay, so in terms of computers, this whole time we've covered the previous study unit that we've covered, we've focused a lot on the blue side, on the blue part, which is processing. All of that stuff about virtual memory, memory management, all of that has a lot to do with how in the background, the CPU will use all of these related components to do its processing. But today, we're going to be talking about a bit about this input and output, okay? What happens during this during these phases of input and output? Okay, so categories of input-output devices. By now, it cannot be that you're in second semester, but you don't know what the input-output devices. I'm sure it might have been covered extensively in your information systems first semester, where you are asked in your assignments, can you list input devices? Can you list output devices? Okay, so um, keyboards, mouses, printers, monitors, to name a few. There's a wide variety of these devices. And some devices can even do more than just inputs. They can do both. They can do input, output, and they can even do storage. Okay. So there are those main classes of these input-output devices. And we say that external devices that engage in input-output with computer systems can be grouped into three categories. Okay, so we have the human readable ones, which are suitable for communicating with the computer user, such as printers, terminals, video display, keyboards, and mouse. So those allow the human readable input-output devices allow the user to interact with the computer. So that's the first classification that we use to classify these input-output devices. And then we have machine readable. Okay, machine readable, suitable for communicating with electronic equipment such as disk drives, USB keys, sensors, and controllers. Okay, so these sort of enable computers to send each other messages or to communicate with each other. And then we have input-output devices that are in charge of communication, okay, suitable for communicating with remote devices. These include modems, routers, digital line drivers, and so forth, okay? So these are the main categories for input, output. And differences in input-output devices. You can remember that in the previous lecture we actually engaged in a very extensive debate about the type of hard drive that you may need to get for your computer. Okay, and so we discussed issues around pricing. Okay, because even with the SSDs that we're debating, you'll find that as you look at the different manufacturers, the prices are going to be different. So maybe you have Toshiba and you also have Gigabyte. They're selling the same, they're both selling an SSD. Uh, they're selling the same capacity, but it's different prices. Okay. So we're not debating here the regular hard drive and the SSD. We're saying they're both SSDs, but it's different manufacturers, and then the price is different. Why is that so? Because there are certain components that you can look at about that particular input-output device, and you're able to measure how sophisticated it is. Okay, for example, let's take the first one, a data rate. There are many differences of magnitude between the data transfer. So how fast? Okay, yes, you're selling me the same capacity drives, but why is the other one cheaper? It could be cheaper, and this is the most popular reason because of the data transfer rates. The other one is transfers data at a higher rate. Okay, so these are some of the significant differences that we find with input-output devices, and this is not only specific to hard drives. I'm just using it as an example because we had spoken about it last week, and application as well. To use the use to which a device is put has an influence on the software. Okay, complexity of control. The effect on the operating system is filtered by the complexity of the input-output module that controls the device. Unit of transfer. What kind of unit does the hard drive use to transfer data? Is it in bytes? Is it in kilobytes? Is it in megabytes? Or is it in gigabytes per second? Okay, so units of measure as well, which ties into the first one, data rate. Okay, data representation. Different data encoding schemes are used by different devices, and then also error conditions. The nature of errors, the way in which they are reported, their consequences, and the available range of responses differs from one device to another. So basically what this is saying is that we can use these components or concepts to measure how effective a particular input device is, okay? And I'm saying to you that the most important one, and that's why I repeat this one, is the data rate, okay? And you can see that this is just an example of a chart and common input-output devices, okay? So something like a keyboard, the data rate for a keyboard would be lower than the data rate for a mouse, but the data rate for a mouse would be lower than the data rate for a modem, okay? So as you go up higher, you're gonna see that the data rate increases, the amount of transfers it can send between the CPU and the actual input-output device itself, okay? So something like gigabyte, if you look at the very top, graphics display, there will be a lot of data being transferred there. Gigabyte Ethernet cable, okay? Transferring your network data. There's going to be a lot of transfer of data there. And a hard drive as well. Hard drive is one of the most busiest components in terms of input-output in the computer. So there's going to be a lot of, if you just look at the top three, you can tell that these are very busy devices. And so the data rate will be very high for them. Organization of the input-output function. Okay, so we have programmed input-output. The processor issues an input-output command on behalf of a process to an input-output module. That process then busy waits for the operation to be completed before proceeding. Okay, so programmed input-output is sort of integrated into software. It's not interrupt driven, it's not triggered by a particular user. Okay, so it's programmed, it's in the software. Maybe the developer of the software said, after step 1, 2, and 3, can you print this report? Can you print this file? So that is a programmed input output. Okay, interrupt driven input output. The processor issues an input-output command on behalf of a process. If non-blocking, processor continues to execute instructions from from the process that is issued to the input-output command. If blocking the next instruction, the processor executes it from the OS, which will put the current process in a block state and schedule another process. Okay, so input, output interrupts. How do they occur? And we've spoken about this. I think this was in your first assignment. Okay, we agreed that input output is the language. Okay, interrupt is a concept that speaks to the fact that certain hardwares may need to interrupt the CPU while it's doing its work. Okay, so interrupt-driven input-output occurs through some sort of external, mostly it's an external force. You pressing as a user, pressing on the keyboard, you're moving your mouse, and the cursor has to move now. It cannot delay for anything. Okay, so that is an interrupt-driven. It's an interrupt request or an electronic. We said the interrupt is an electronic signal that is actually sent to the CPU. Okay, so we have that programmed interrupt-driven input-output. Then we also have direct memory access. A DMA module controls the exchange of data between the main memory and the input-output module. This one I will save for the later slide. So evolution of the input-output functions. How has this input-output function evolved over the number of years? Well, previously what you'll notice is that processor directly controls a peripheral device. That's the olden day computers where there was a lot of serial processing, okay? So the processor directly controls a particular peripheral device. And then we have step number 2 in the evolution, a controller or input-output module is added, okay? Then in step number 3, same configuration as step 2, but now interrupts are employed. So these hardwares, external devices or input-output devices can now initiate interrupts or interrupt the CPU while it's doing its work, okay? Then step number 4, the input-output module is given direct control of memory via DMA. So step 4 in the evolution was the introduction of DMA. Not only, so interrupts were introduced in step number 3, then step number 4 we had DMA technology. And then step number 5 in the evolution process says the input-output module is enhanced to become a separate processor with a specialized instruction set tailored for input-output, okay? And then the last evolution is the input module has a local memory of its own and is in fact a computer in its own right. So what does this mean? It means we moved away from processors connecting directly to the peripheral devices, okay? And now we have these input-output modules, okay, which manage input-output requests. And so now we can use the concept of buffering certain input-output requests. And if you look at the graphics card, okay, a graphics card is one type of input-output device which will come with its own memory on board. Okay, so it has its own localized technology. Not that it won't use the system-based memory, but it comes with its own one, that is example of step number 6, where the actual input-output module it's a computer in its own right. For the mere fact that it will have some sort of chip there, which is working like the CPU, and it will have onboard memory, okay, means that it's in the step number 6 of the evolution process. And so we have input-output ports. And if you notice at the back of your PC, you're most likely to see something like this. And this is the interface at which these peripheral devices, external devices, or input-output devices actually plug in to the computer, okay? If you're old enough, you may recognize number 1 and 2. We call them PS2, not Sony PS2, not the PlayStation. It was just called PS2. I'm sure it stands for something, but it's just called PS2. And Then we also have all of these other funny ones, D connectors, number 3, 4, 5, then we have 6 as well. Number 8 is very common and still available in modern computers. And then we also have 7, which is for LAN connections. And we have 9, okay? 9 also very popular for output interfacing, your audio driver, okay? So you're able to play music and so forth. Now, if just by looking at, let's compare 1 and 2 and 8, okay? So before, we had all of these PS2 based keyboards and PS2 based wired keyboards, okay? So the connection, I think the green was for the mouse and the purple was for the keyboard. So they've changed it now. They've changed it, and now our keyboards and mouses connect via what? Via number 8, which is the USB ports. So by changing this interface, what is the difference? What is the improvement? It will be the data rate. Okay, the data rate will then be improved because USB technology definitely can transfer data as an interface faster than these PS2 interfaces, olden day technology. Okay, so you can see the concept that the technology is evolving, and even the input-output modules and input-output interfaces have to also evolve in the same manner. So we also have disk input-outputs. So disk input-output includes read or write or input-output operations defined in kilobits per second involving a physical disk. In simple words, it is the speed with which the data transfer takes place between the hard disk drive and the RAM, or basically it measures active disk input-output time, okay? So we say disk input-output has the greatest impact on overall systems performance, okay? So and this also goes back to our in terms of the input-output devices, okay? This is excluding the CPU, excluding the RAM, okay? So if we look at the input-output devices as a whole, including these disks, they are the ones that have the greatest impact, okay, on overall system performance. It doesn't matter if you bought a cheap keyboard, it doesn't matter if you bought a cheap mouse, it doesn't matter if you bought cheap speakers. They'll still achieve the same concept, but if you buy a cheaper hard drive, then that one has implications on performance. Hence, we said an SSD would be a better improvement. Okay, so the hard drive does have a say on overall systems performance. It is a measure of performance and is thus needed to characterize the storage devices like our hard drives, regular hard drives, and our SSDs, and also in our storage area networks. So for those of you who may have not understood what the fuss was about last week, you will be able to see the technology behind the regular hard drive and what we call the SSD, or the solid state drive, okay? And with the normal hard drive, there's this mechanism inside. It's a spinning mechanism. That's why the regular hard drives are normally thicker and they make a lot of noise, okay? And in comparison, you can see with the SSD, it's actually smaller and it has a lot of semiconductor chips, the black chips that you see, or you can also refer to them as NAND flash memory. Okay, and there's no spinning mechanism, which means it's going to reduce the amount of noise as well, and the hard drive is going to be smaller in size. Okay, now also they mentioned something about shock resistance up to 55G and shock resistance up to 350G non-operating. So when it's operating, when it's working, the amount of shock it can take, okay, is 55. And the amount of shock it can take when it's non-operating is 350. But in comparison, you can see the amount of shock that an SSD can withstand. What do we mean by shock? Okay, so if you bump your laptop, or you drop your laptop, whatever, while your computer is operating, remember that you can see that the HDD has what we call platters inside, and it has the actuator arm. So if you bump that device while it's operating, the possibilities of your hard drive malfunctioning are very high as compared to the SSD. Okay, because it doesn't have a spinning mechanism inside. You bump it, it's gonna have a higher resistance to shock. Okay, so those are the common significant difference besides just the speed, the difference in speed between the regular HDD and the SSD. There's the other things in the background that differ. So direct memory access. So DMA is also a component that is embedded on the motherboard, and this component is there to it sort of mimics the CPU. Okay, so DMA unit is capable of mimicking the CPU, the processor, and taking over control of the system bus, just like how the processor would. Okay, you can see within the particular DMA components, there are registers. Don't worry about the other stuff at the moment, but we spoke about registers and the importance of registers, having these registers. Okay, so registers are some sort of local storage that keeps track of things that need to be executed. So because it's representing an input-output module, okay, it could be representing a hard drive, it could be representing whatever particular input-output device may be requiring memory allocations, then it's going to have registers, because registers are like internal offices of these components where they do their work or store things that need to be done still. Okay, so direct memory access, what I want you to get out of the slide, that this is a separate component on the CPU, and it's there to mimic it's like a dummy CPU. And so direct memory access enables data to be exchanged between the main memory and the input-output devices. The central processing unit is only involved at the beginning and end of the transfer. So you can see in the diagram that DMA will have its own path. It will have its own path through the bus, through the system bus, or what you can call the data bus. It will have its own unique path, and we refer to this concept as bypassing. Okay, so it's bypassing the CPU, because if this was regular input output, then or interrupt request, if this was an interrupt request, then it will have to go through only one path. Okay, so in that sense, that's why we say that DMA mimics the CPU, because it has an alternative or a shortcut to the main memory, and only limited technologies can operate using DMA. So we discussed some of these registers before, and I think it was part of Unit 1. And I just want to remind you again of the first two. We have the memory buffer register, and we have the memory address register. Okay, so the memory buffer register contains a word to be stored in memory or sent to the input-output unit, or is used to receive a word from memory or from the input-output unit. Okay, and then we have the memory address register, specifies the address in memory of the word to be written from or read into the memory buffer address. Okay, so which brings us to our next concept. Buffering. It's a term that we use often, but what does it mean? What is buffering, and how does it relate to input-output? So perform input transfers in advance of requests being made, and perform output transfers sometime after the request has been made. So through buffering, we put input-output requests in a localized area, you can also look at it as a queue. Okay, while they are waiting their execution, having them in a queue ensures that that particular device that's executing them will be able to access it faster, that we have that locality of reference, okay, as opposed to if it was all located outside where it has to go through the whole process of retrieving it again and placing it in main memory. So a buffer is contained somewhere there as part of the registers, not as part of the CPU registers, as part of the main memory registers, okay? Because remember that from this table, there are registers that are part of the CPU, and then there are registers that are part of the first two are part of the main memory, okay? So there's a buffer there, which has a queue of all of these inputs, outputs. And without a buffer, the OS directly accesses the device when it needs it. This can lead to a bottleneck, okay? Too much coming in, not enough being put through. Okay. And the reason for this is because it's happening, there's no buffer, there's no locality of reference, which means we go one by one. We do it, we finish it, and so forth. But in terms of a buffer, we have locality of reference, which means everything we need to do is in the same place. It's just a matter of finishing the first one, then you move on to the next one quicker. We don't have to now go and retrieve the next one again. So no buffering is an ancient concept, and it leads to a lot of, I would say, serial processing. So then we say the use of buffering technique that smoothens out peaks in input-output demand. With enough demand, eventually all buffers become full and their advantage is lost. Okay, so the buffer, just like the cache memory, is a small unit. It can't store everything, but maybe it can store the first 10. Okay, after it's full, it doesn't have any more space. It needs to start to using the algorithms we've spoken about a lot. It needs to start to make space for other things. So it may apply the concept of first in, first out in that particular order. So it's going to slowly clear the buffer is going to clear itself based on a particular algorithm. When there's a variety of input, output, and process activities to the servers, buffering can increase the efficiency of the OS and the performance of individual processing. Okay, so when the buffer is full, becomes too full, its advantage is lost, and it has a big advantage on the execution of input output requests, as they say in the second point, as opposed to having these individual processing running in series. So then we also have a single buffer. Okay, so this basically the operating system assigns a buffer in main memory for input-output requests. So this is just one buffer location within the main memory. And so if we say a buffer can store 10 processes at a time, which means here with single buffering you can only store 10. Okay, and then that one is cleared for the next 10 to arrive. And then we have double buffering. Use 2 system buffers instead of 1. A process can transfer data to and from one buffer while the operating system empties or fills the other buffer, also known as buffer swapping. So here we have a backup buffer. So the first one is full, okay? Then so the first 10 have already been allocated in the first buffer. Then it moves on to the next one. Let's use the next one while this one is still being cleared. Okay, so that's the concept of double buffering. And then we also have circular buffering, where more than 2 buffers are used. Okay, so when there's more than 2 buffers used, we don't refer to it as double buffering, we refer to it as circular buffering. Now, the operating system has 2 or more buffers to work with, okay, and it can rotate these, and this is good for instances where a particular memory has to keep up with a particular process. Okay, so we say use 2 system buffers instead of 1. A process can transfer data to and from one buffer while the operating system empties or fills the other buffer. Okay, so this is not the accurate description of this circular buffering, but how it actually works is that it will work in a circular manner, okay, using arrays. And this is good for when a particular process needs real-time processing, okay? Because the components of this particular process will keep on being exchanged between these different buffers, okay? So if the first one is being cleared, then we move it to the next one, okay? If the second one is being cleared, then we move the process to the next one. It has to keep up with the process as it evolves. So a part of a process may be moving between these different buffers as they are being emptied in a circular manner using an array. So maybe this one will be array 0, array 1, and array 2, and it will keep on rotating between those different buffers. So then we have the next topic, which is redundant array of independent disk, or also commonly referred to as RAID. Okay, not RAID the insect killer, RAID, redundant array of independent disk. RAID is a set of physical disk drives viewed by the operating system as one single logical drive. So the operating system perceives it as one single drive, but in actual fact, it's multiple hard drives within the same system. Okay, and redundant disk capacity is used to store parity information, which guarantees data recoverability in case of a disk failure. Data are distributed across the physical drives of an array in a scheme known as striping. Okay, sometimes they refer to it as striping or stripping. Okay, but let's just call it striping for now. So RAID, then we can refer to RAID as a backup utility. It's a backup utility for the computer. We are able to implement multiple disks to either duplicate our data or stripe our data. There are different levels to this RAID. We won't cover all of them. We'll probably, for the purpose of this lecture and time, we're probably going to cover, I think, up to the first 3. And then we'll just look at the other ones in Thursday's lecture. But the 2 most commonly used or commonly debated levels of RAID is RAID 0 and RAID 1. Okay, so RAID 0 is referred to as disk striping. Not a true RAID because it does not include redundancy to improve performance or provide data protection. User and system data are distributed across all the disks in the array. Logical disk is divided into stripes. Okay, so if you look at the diagram here, the reason why they call RAID 0 not a true RAID, because the data is distributed. It's not duplicated, it's distributed. If you're telling me about a backup is something that there has to be duplicate copies of what you're backing up. So why is RAID level 0 still being called RAID if it doesn't actually duplicate the data, but it only strips it between multiple arrays? And you can see here, there's array 0 again, array 1, 2, and 3. Okay, there's 4. Or in simple terms, let's say there's 4 hard drives. There's 4 hard drives in front of you now. And so 25% of the data will be saved to hard drive 1, 25 to the next one, 25, 25. So what then happens? It means that if we lose some, we don't lose everything. That's basically what it means. But in terms of how good of a backup mechanism this is, I don't think it's a really good one because we still lost 25% of our data. Okay, so disk stripping happens at RAID level 0. So what are the pros and cons of this RAID level 0, provides better performance. Why does it provide better performance? Because the information is not duplicated, but it is distributed between multiple disks, which means the process of what you can call backing up will occur faster. Utilize all storage capacity. Okay, implementation is very easy. What are the disadvantages of using RAID 0? It's not fault tolerant. If one of the drives malfunctions, okay, it's not true that the whole data is lost, okay, but the data within that particular array will be lost. Not everything, okay, because obviously it's RAID, it's multiple disks, and we say in terms of disk stripping, it's going to be, let's say, 4 disks, and each one is storing 25% of the data, so it's distributed between those 4 disks. So if we lose one, then we don't lose everything, but we lose whatever was in that drive. So we still can't refer to it then as fault tolerance. It's not fault tolerance because we still lost something. Okay, cannot be used to systems that are critical. Yes, it has its benefits because it has better performance, and it's definitely cheaper. It's definitely cheaper because if you're storing only 25%, it means that the time at which it will take that hard drive to reach its full capacity is going to be reduced. Okay, so those we can say it has its benefits, but it's not good for mission critical systems. And then we have RAID level 1, which this one is referred to as disk mirroring, okay, or duplication. So again, we have 4 arrays, and then the arrays in blue are the original ones, the original drive. Then we also have the arrays in gray, which are the duplicates, the exact duplicates for each of these hard drives. Okay, so redundancy is achieved by the simple expedient of duplicating all the data. There is no write penalty. When a drive fails, the data may still be accessed from the second drive. Principal disadvantage is cost. Okay, and in the next slide, these advantages and disadvantages are further highlighted for RAID level 1. We say advantage is that it is very fault tolerant if you're comparing it to the first RAID, which is RAID level 0, because there is an exact copy of array 0 in arrays 0's duplicate or RAID disk. Okay, so there's more fault tolerance. The technology is used is very simple. What are the disadvantages of RAID level 1? Limited storage capacity because data gets written twice. Does not allow hot swapping of failed drive. Okay, so you can't just change the failed drive because then you're going to mess up the duplication process, which is a very challenging task for implementing RAID level 1. And also, you're going to be using a lot of storage. So yeah, you're going to be using a lot of storage for duplication. And then we also have RAID level 2, makes use of parallel access technique. Data striping is used. Typically, a Hamming code is used, or we also refer to this as parity. A parity bit is used. Effective choice in an environment in which many disk errors may occur. Okay, so this one still, RAID level 2 still uses the concept of disk stripping. However, the difference is, unlike RAID level 0, this one will have a backup hard drive linked to each array, which has error correction data. So whenever data wasn't stored properly in array 0, there will be a backup drive that's storing what we call parity bits to correct those errors. So each of the drives in the array, or the blue drives, will have their own dedicated parallel error correction disk, which is there to keep track of any errors in data for recovery purposes only. Okay, so that's the significant difference between RAID level 2 and RAID level 0, but they both use the same concept of striping as opposed to duplication. And then you also have RAID level 3, okay? So unlike RAID level 2, this one will only have one shared parity disk, correcting the errors for all the disks in the array, correcting the errors for array 0, array 1, array 2, and array 3, okay? One shared disk. So it requires only a single redundant disk, no matter how large the disk array is, employs parallel access with data distributed in small stripes, can achieve very high data transfer rates, okay? So again, the significant difference here is the error or parity bit, which is there to correct errors in data, and similar to level 2. The only significant difference is that with level 2, it's going to be more expensive because there's a dedicated drive for each drive in the array to ensure redundancy or error correction. Okay, so in conclusion, the input-output architecture is the computer system's interface to the outside world. A key aspect of input-output is the use of buffers that are controlled by input-output utilities rather than by application processes. So we say the process of buffering suits out the differences between the speeds. Okay, the use of buffers also decouples the actual input-output transfer from the address space of the application processes. Disk input-output has the greatest impact on overall system performance. Two most widely used approaches in disk scheduling and disk cache. That one we'll cover extensively in Thursday's lecture, disk scheduling. A disk cache is a buffer, usually kept in main memory, that functions as a cache of disk block between disk memory and the rest of the main memory, okay? So that concludes the topic of today, which is input, output management, and disk scheduling, okay? So let me just stop the recording there.